Welcome everyone. In this chapter, we will study rotational equilibrium and the dynamics of rotational motion. By the end of this chapter, you will understand how objects rotate, why they remain in equilibrium, and how to analyze rotational motion using physics principles. In this chapter, we will cover 5 main topics. First, we will learn about the center of gravity, which tells us where the weight of an object effectively acts. Next, we introduce torque, the rotational equivalent of force. We then study the conditions required for a rigid body to remain in equilibrium. After that, we will discuss moment of inertia, which describes how difficult it is to change an object's rotational motion. Finally, we will combine all these ideas to study the dynamics of rotational motion using Newton's second law for rotation. In rotational motion, where a force acts is just as important as how large the force is. Consider the seesaw shown in the figure. Both people exert downward gravitational forces, but because these forces act at different distances from the pivot, they produce different rotational effects. Notice that the weight of the plank itself acts through its center of gravity, not at every point along the plank. Therefore, when analyzing rotational motion, we must always identify both the magnitude and the point of application of every force. Every object is made up of many tiny particles, and each particle experiences its own gravitational force. Instead of considering all these individual forces, we can replace them with a single equivalent force acting at the center of gravity. If the positions and masses of all particles are known, the coordinates of the center of gravity can be calculated using the weighted average formula shown on the slide. In other words, particles with larger masses contribute more to the location of the center of gravity. The location of the center of gravity depends on 2 factors: the distribution of mass and the gravitational field acting on the object. For example, the center of a square is at its geometric center, the center of a circle is at its center, and the center of a uniform triangle is located along its line of symmetry. These are useful results that we will frequently apply when solving rotational equilibrium problems. Besides calculation, the center of gravity can also be determined experimentally using the plumb line method. When an object is suspended freely, its weight and the tension in the string act along the same vertical line. Therefore, the center of gravity must lie on this line. By suspending the object from different points, the intersection of the vertical lines gives the location of the center of gravity. In this example, all the particles lie on the x-axis, so the y-coordinate of the center of gravity is 0. We only need to calculate the x-coordinate using the center of gravity equation. After substitution, the center of gravity is 0.136 meters from the origin. Try solving this question yourself. Take the fulcrum as the origin, so the center of gravity of the system is at x equals 0. Apply the center of gravity equation to determine the position of the 75 kilogram man. The correct answer is 1.47 meters. We now introduce torque, which is the turning effect of a force. Just as force causes linear acceleration, torque causes angular acceleration. Torque is calculated using the perpendicular component of the force. Torque equals r multiplied by F perpendicular. By convention, counterclockwise torque is positive, while clockwise torque is negative. When the applied force is at an angle, first resolve it into perpendicular and parallel components. Only the perpendicular component produces torque. Therefore, torque is calculated using tau equals Rf sin theta. Finally, determine whether the torque is clockwise or counterclockwise before assigning its sign. Instead of resolving the force, we can also resolve the distance from the axis of rotation. The perpendicular distance from the axis to the line of action of the force is called the lever arm. Using the lever arm, torque is simply tau equals lever arm multiplied by the force. Both methods give the same answer, so use whichever is more convenient. In this example, the force is applied at an angle of 60 degrees to the horizontal. Since the angle is measured from the horizontal, we first resolve the force into horizontal and vertical components. Notice that the horizontal component acts along the door, so it passes through the hinge and does not produce any torque. Only the perpendicular component, 300 sin 60, contributes to rotation. Therefore, the force tends to rotate the door counterclockwise, so the torque is positive 520 Nm. Now, let's try one together. Before calculating, identify which method you want to use. You can either resolve the force into components or resolve the distance into perpendicular and parallel components. Remember, torque always depends on the perpendicular component and the distance from the pivot, which is point A, take about 2 minutes to solve it individually, then we'll discuss the solution together. When more than one force acts on an object, we calculate the resultant torque by considering each force separately. First, ignore any force acting through the rotational axis, because it produces zero torque. Next, resolve each force into perpendicular and parallel components. Again, only the perpendicular component creates torque. Then determine the direction of rotation. In this chapter, we'll take counterclockwise as positive and clockwise as negative. Finally, add all torques together with their signs. The result is NRE summation tau equals minus F1 cos theta 1 d1 plus F2 d2. Finally, don't confuse resultant force with resultant torque. For resultant force, we include every force, even those acting through the rotational axis, and distance is not involved. However, for resultant torque, the distance from the rotational axis is essential, and forces acting through the axis produce zero torque. Another important difference is that the net force is independent of the choice of rotational axis, whereas the net torque depends on where the rotational axis is chosen. Keep these differences in mind because students often mix up these two concepts. In this example, we are asked to find the net torque about point O first. Choose point O as the rotational axis. Then, resolve each force into perpendicular and parallel components. Any force acting through the rotational axis or parallel to the beam produces zero torque and can be ignored. Next, determine the direction of rotation for the remaining forces. The 25N force produces a counterclockwise torque, while the 10N force produces a clockwise torque. Finally, sum all the torques with the correct sign. The resultant torque is 29.6 Nm counterclockwise. In part B, we are asked to find the net force acting on the beam. Unlike torque, all forces must be included, even those acting through the rotational axis. Resolve each force into its horizontal and vertical components. Then, sum the forces separately along the x direction and y direction. From the calculation, the net horizontal force is 0.684 N to the right, while the net vertical force is 2.98 N downward. Remember, when finding resultant force, the position of the rotational axis is not important. Only the force components are considered. Now, try this question on your own. Derive the expression for the net torque about point O, as well as the horizontal and vertical components of the net force acting on the rod. Start by identifying the rotational axis at point O. Calculate the torque produced by each force, assign the correct sign based on its direction of rotation, and then sum all the torques. Next, resolve all the forces into their x and y components, and apply Newton's second law by summing the forces in each direction. For a rigid body to be in static equilibrium, two conditions must be satisfied. First, the net force must be zero, so the object has no linear acceleration. Second, the net torque must also be zero, so the object does not rotate. When solving equilibrium problems, both conditions must be applied together. One useful point to remember is that if an object is in equilibrium, the net torque is zero about any chosen rotational axis. This allows us to select the most convenient axis to simplify our calculations by eliminating unknown forces. When solving equilibrium problems, always follow these three steps. First, draw a free body diagram, showing all the forces and their points of application. Second, choose a rotational axis that eliminates as many unknown forces as possible. In this example, selecting the lowermost point is the most convenient choice. Finally, apply the equilibrium condition by setting the net torque equal to zero. Remember to assign the correct sign to each torque based on its direction of rotation. Once the torque equation is established, you can then use the force equilibrium equations to determine the remaining unknowns. After drawing the free body diagram, apply both equilibrium conditions. First, set the sum of forces in the x and y directions equal to zero to obtain the force equations. Then, set the sum of torques about the chosen rotational axis equal to zero to obtain the torque equation. Notice that choosing the rotational axis only simplifies the torque equation by eliminating unknown forces. Those unknown forces must still be included in the force equilibrium equations. Finally, remember that torque can be calculated by resolving either the force or the distance. In this example, the distance is resolved to obtain the torque equation. Whenever a support prevents the motion of a rigid body, it produces a reaction force. The direction of the reaction depends on the type of support. A smooth surface prevents motion only in the perpendicular direction, so it provides a single normal reaction. A rough surface prevents motion in both the perpendicular and parallel directions, producing both a normal force and a frictional force. A pin support also prevents motion in both the horizontal and vertical directions. Therefore, its reaction force is represented by two components, R, X and Y. Since the directions of these reaction components are usually unknown, we simply assume positive directions. If the calculated value is negative, it means the actual direction is opposite to our assumption. Let's begin by drawing the free body diagram. There are four forces acting on the beam: the reaction force at the pin support, the tension in the cable, the 600 N weight of the person located 1.50 meters from the wall, and the 300 N weight of the beam, which acts at its midpoint because the beam is uniform. Finally, resolve the reaction force and the tension into their horizontal and vertical components before proceeding with the equilibrium analysis. Next, we need an equation to determine the tension, T. To eliminate the unknown reaction forces, choose the pin support as the rotational axis. Then, apply the torque equilibrium condition, N summation tau equals 0. The clockwise torques are produced by the 600 N and 300 N weights, while the vertical component of the tension produces a counterclockwise torque. This torque equation can then be used to solve for the tension in the cable. Once the tension is known, we can determine the reaction force at the pin support. Apply the force equilibrium condition, where the net force in both the X and Y directions is 0. From the horizontal force balance, we obtain an equation for Rx. From the vertical force balance, we obtain another equation for Y. Solving these two equations gives the horizontal and vertical components of the reaction force. Now, try this equilibrium problem on your own. First, draw the free body diagram and choose the fulcrum as the rotational axis to eliminate the normal force. Apply torque equilibrium to determine where the 75 kg man should sit. Then, use the force equilibrium equation to calculate the normal force exerted by the fulcrum. Pause the video and attempt the solution before checking the answers shown on the slide. Now, try this ladder equilibrium problem. First, draw the free body diagram and choose the bottom end of the ladder as the rotational axis. This eliminates the normal and frictional forces from the torque equation. Apply torque equilibrium to determine the force exerted by the wall. Then, use the horizontal and vertical force equilibrium equations to calculate the normal force and the frictional force exerted by the floor. We now introduce the moment of inertia, denoted by I. Just as mass measures an object's resistance to linear acceleration, the moment of inertia measures its resistance to angular acceleration. The moment of inertia depends on two factors: the mass of the object and how the mass is distributed relative to the rotational axis. The farther the mass is from the axis, the greater the moment of inertia, and the harder it is to rotate the object. For a point mass, the moment of inertia is simply I equals mr2, where r is the distance from the rotational axis. For an extended object, the size and mass distribution cannot be ignored. Its moment of inertia depends on both the shape of the object and the location of the rotational axis. For a composite object, the total moment of inertia is simply the sum of the moments of inertia of all its individual parts. In this slide, we compare the moment of inertia of several common objects. A simple rule to remember is that the farther the mass is distributed from the rotational axis, the greater the moment of inertia. In other words, the object becomes more difficult to rotate. Compare a hoop and a solid disk. Although they have the same mass and radius, the hoop has a larger moment of inertia because most of its mass is concentrated at the outer edge. In contrast, the solid disk has more mass closer to the center, making it easier to rotate. The same idea applies to a solid sphere and a thin spherical shell. Since the shell has more of its mass farther from the axis, it has a larger moment of inertia than the solid sphere. Now look at the long thin rod. The rotational axis can significantly affect the moment of inertia. When the rod rotates about its center, it is easier to rotate because the mass is more evenly distributed on both sides of the axis. However, when it rotates about one end, much of the mass is farther from the axis, so the moment of inertia increases. Therefore, for objects with the same mass, the moment of inertia is generally smallest when the rotational axis passes through the center of mass. Likewise, hollow objects usually have a larger moment of inertia than solid objects of similar shape and size because more of their mass is located farther from the rotational axis. In this example, the rods have negligible mass, so we only consider the four particles. Since each particle is the same distance from the rotational axis, calculate the moment of inertia of each particle and then add them together. The total moment of inertia of the system is 0.250 kg/m². Now, try this question yourself. This time, the rotational axis passes through the two 0.20 kg particles. Since these two particles lie on the axis, they do not contribute to the moment of inertia. Only the two 0.30 kg particles contribute, so calculate their individual moments of inertia and add them together. We now move on to the dynamics of rotational motion. Many concepts from linear motion have direct counterparts in rotational motion. For example, force corresponds to torque, displacement corresponds to angular displacement, kinetic energy becomes rotational kinetic energy, and linear momentum becomes angular momentum. Throughout this chapter, you'll notice that many equations for rotational motion are closely related to those for linear motion. Understanding these analogies will make rotational dynamics much easier to learn. Just as a net force produces linear acceleration, a net torque produces angular acceleration. The amount of angular acceleration depends on the net torque applied and the object's moment of inertia. When solving rotational dynamics problems, first draw a free body diagram, identify all the torques about the rotational axis, and then apply Newton's second law for rotational motion. Unlike equilibrium problems, the rotational axis is usually fixed and clearly defined, making the torque analysis more straightforward. In this example, we combine linear motion and rotational motion. First, draw separate free body diagrams for the bucket and the reel. Apply Newton's second law for rotation to the reel by taking moments about its center. Then, apply Newton's second law for translation to the falling bucket. Finally, because the cable does not slip on the reel, the linear acceleration of the bucket equals the tangential acceleration at the rim of the reel. These three equations can then be solved simultaneously to determine the tension, linear acceleration, and angular acceleration. Now, try this question on rotational dynamics. Draw the free body diagram of the rod and identify the pin support as the rotational axis. The weight of the rod acts at its center of mass, producing the only torque about the pivot. Then, apply Newton's second law for rotational motion, together with the moment of inertia of a rod about one end, to determine the angular acceleration. Just as a moving object possesses translational kinetic energy, a rotating object possesses rotational kinetic energy. Notice the close analogy between the two equations. In linear motion, mass is replaced by moment of inertia, and linear speed is replaced by angular speed. Therefore, the equation for translational kinetic energy is directly translated into the rotational form. If an object is both translating and rotating, such as a rolling ball, it possesses both forms of kinetic energy. Hence, the total kinetic energy is simply the sum of the translational and rotational kinetic energies. Conservation of energy also applies to rotational motion. As an object rolls down a slope, its gravitational potential energy is converted into both translational and rotational kinetic energy. Unlike a sliding object, a rolling object must share its energy between moving forward and spinning. As a result, it gains less translational kinetic energy and moves more slowly. This explains why an object sliding without friction reaches the bottom first. It uses all of its potential energy for translational motion. The shape of the rolling object also matters because different shapes have different moments of inertia. Objects with smaller moments of inertia require less energy to rotate, so more energy is available for forward motion, allowing them to roll faster. Just as in linear motion, the work-energy theorem also applies to rotational motion. The work done by non-conservative forces changes the kinetic and potential energies of the system. In linear motion, we calculate work as force multiplied by displacement. In rotational motion, force is replaced by torque, and displacement is replaced by angular displacement. Therefore, whenever an object rotates because of a torque, we use the rotational form of work instead. This is the rotational analog of the linear work equation and will be useful when solving energy problems involving rotating objects. This question combines conservation of energy with rotational motion. As the sphere rolls down without slipping, its gravitational potential energy is converted into both translational and rotational kinetic energy. Start by writing the conservation of energy equation. Then, recall the moment of inertia for a solid sphere and use the no-slip condition to relate the linear speed to the angular speed. Finally, substitute everything into the energy equation and solve for the speed of the sphere at the bottom. Give this a try before checking the answer. Finally, just as linear motion has momentum, rotational motion has its own equivalent called angular momentum. It depends on both the object's moment of inertia and its angular speed. This is another direct analogy between linear and rotational motion. Linear momentum becomes angular momentum. One important difference is that, unlike kinetic energy, linear and angular momentum have different units. Therefore, they represent different physical quantities and cannot be added together. In the next section, we'll see why angular momentum is such an important conserved quantity in rotational motion. Just as linear momentum is conserved, angular momentum is also conserved when there is no external torque acting on the system. This means that if the moment of inertia changes, the angular speed must change to keep the angular momentum constant. A familiar example is a ballerina. When she stretches her arms outward, her moment of inertia increases, so she spins more slowly. When she pulls her arms inward, her moment of inertia decreases, causing her to spin much faster. This is a classic demonstration of the conservation of angular momentum. This question combines two concepts: conservation of angular momentum and the work-energy theorem. First, since there is no external torque, apply conservation of angular momentum to determine the new angular speed after the student pulls the weights inward. Then, use the work-energy theorem to calculate the work done by the student. Notice that the rotational kinetic energy increases, and this extra energy comes from the work done by the student's muscles. This chapter shows that almost every concept in linear motion has a corresponding concept in rotational motion. Displacement becomes angular displacement, velocity becomes angular velocity, and acceleration becomes angular acceleration. Similarly, force is replaced by torque, and mass is replaced by moment of inertia. Newton's second law, work, kinetic energy, momentum, and even conservation laws all have rotational counterparts. Once you understand these analogies, learning rotational motion becomes much easier because the mathematical structure is very similar. As you continue your studies, try to recognize these pairs. It is one of the most powerful ways to understand rotational dynamics. Let's conclude this chapter with a quick summary. We began by introducing the center of mass and torque, which are the foundation for analyzing rotational motion. Using these concepts, we studied the conditions for rigid body equilibrium, where both the net force and net torque must be zero. Next, we introduced the moment of inertia, the rotational equivalent of mass, and learned the standard formulas for common objects such as rods, cylinders, and spheres. Finally, we explored the dynamics of rotational motion, including Newton's second law for rotation, rotational kinetic energy, and angular momentum together with its conservation. Throughout this chapter, remember the key idea: rotational motion is closely analogous to linear motion. Once you understand the parallels between the two, solving rotational problems becomes much more intuitive. Thank you. End of this chapter on rotational equilibrium and dynamics of rotational motion. Today, we learned how rotational motion parallels linear motion, from equilibrium and torque to moment of inertia, rotational dynamics, energy, and angular momentum. I encourage you to review the analogies between linear and rotational motion, as they are the key to mastering this topic. Thank you for your attention. If you have any questions, feel free to ask. Otherwise, I'll see you in the next lecture. Have a great day.